Hi everyone, this is Kiranmay from H&S department. Today in this session, we are going to discuss about a P-type extrinsic semiconductor. Under this session, we are going to discuss about a carrier concentration of P-type extrinsic semiconductor, Fermi energy, and the variation of Fermi level with respect to the temperature and carrier concentration. First of all, what is a P-type extrinsic semiconductor? See, a trivalent element which is having 3 valency electrons in its outermost orbital is added to a pure intrinsic semiconductor in small traces. Then that semiconductor is known as P-type extrinsic semiconductor. Out of all the 3 electrons, these are engaged in covalent bonding with 3 neighboring semiconductor atoms, and it needs 1 more electron to get bonded up with 4th semiconductor atom. And to complete this bonding, it needs 1 more electron and it is ready to accept that electron. Hence, the trivalent elements are called as acceptors, and the level belonging to those acceptor atoms are called as acceptor level, which is just above the valency band. Even if you give a relatively small energy also, electrons from the valency band can excite easily from valency band to acceptor level rather than from valency band to conduction band, because the gap between valency band to conduction band is very high. So small temperature rise cannot rise the electron from valency to conduction band, but that small temperature is enough to move an electron or to lift an electron from valency band to acceptor level. Hence, at small temperatures itself, more and more carriers, more and more electrons will be excited from valency band to acceptor level, leaving holes in the valency band. Hence, the majority carriers of a P-type extrinsic semiconductor are holes and the minority carriers are electrons. Now on the screen, you can observe a P-type extrinsic semiconductor made of germanium doped with boron. Coming to the energy band diagram of a P-type extrinsic semiconductor, at 0 degree Kelvin, as of the intrinsic semiconductor, it will behave like an insulator itself. But as you increase the temperature, what happens? The electrons from the valency band will be excited from valency band to acceptor level, making those acceptor atoms to be negatively ionized. After accepting that electron, the acceptor atom will become negatively ionized and holes will be left over in the valency band. So here, the condition for the P-type extrinsic semiconductor can be given as at small temperatures, the number of holes in valency band is equal to number of negatively ionized atoms in acceptor level. Negatively ionized atoms in acceptor level. So by using this condition, we are going to derive an expression for carrier concentration of P-type extrinsic semiconductor. Before the derivation, let us take a semiconductor material which is doped with Na number of acceptor atoms, and the acceptor concentration is Na, and they are present in an energy level Ea, which is just above the valency band. Okay, if you increase the temperature, acceptor atoms get ionized and electrons from valency band move to vacant sites of acceptor level, leaving holes in the valency band. As per the intrinsic semiconductor, the density of holes in the valency band is given by P into 2 pi m h star kt by h square power 3 by 2 exponential EV minus EF by kt. This is the density of holes in valency band. In the before slide, as I told you, we need number of holes in valency band and also the number of negatively ionized atoms in acceptor level. So we had the number of holes in valency band, but we need to find out the number of ionized atoms in acceptor level. That can be given by acceptor concentration into probability function. The probability function from statistical mechanics can be written as f of E is equal to 1 by 1 plus exponential E minus EF by kT. Since energy is much greater than Fermi energy, E minus EF will be much greater than 1. Therefore, 1 can be neglected from the denominator. So left over with 1 by exponential function. So if you get this exponential function from denominator to numerator, minus 1, so will be there. If you multiply it, e power EF minus E by kT. This is the probability function. Now in place of E, if you substitute EA, then NA F of EA is equal to NA exponential EF minus EA by kT. This is the number of ionized atoms which are present in the acceptor level. So now just equating the density of holes in valency band with density of ionized acceptors, then and getting exponential functions onto the one side, just taking the constants onto the other side, you'll have like a formula like e power A by e power B. This is nothing but e power A minus B. So just writing exponential EV minus EF by KT minus EF minus EA by KT. So on the left hand side, if you observe that, this is like the LCM is very same. Just rearranging the terms, you'll get EV plus EA by KT minus 2 EF by KT, that is equal to the constant NA by 2 into 2 pi m h star KT by h square power 3 by 2. Now again, if you apply logarithm on both sides, a logarithm and exponential function will cancel each other. So you're left with EV plus EA by KT minus 2F by KT is equal to log of this term. Again, KT is the LCM. If you take KT as LCM and take it onto the other side, you are left with EV plus EA minus 2EF is equal to KT log the constant value. Okay, again take EV plus EA from take 2EF from left hand side to right hand side and get KT onto the other side. You'll get minus 2EF is equal to EV plus EA minus KT log NA by 2 into 2 pi m h star KT by h square power 3 by 2. Again, if you get 2 from left hand side to right hand side, you will be left with EV plus EA by 2 minus KT by 2 log NA by 2 into 2 pi m h star KT by h square power 3 by 2. This is in case if the temperature is 0 degree Kelvin, the second term will become 0, then EF is equal to EV plus EA by 2, which means that at 0 degree Kelvin, you'll have a Fermi level which is just in between valency level to acceptor level, just in between valency level to acceptor level. Now to find out the whole concentration in valency band, we need an exponential function. For that, just substitute Fermi energy in this exponential function. EV minus EF. In place of EF, just derived expression EV plus EA by 2 minus of minus will become plus KT by 2 log NA by 2 into 2 pi m h star KT by h square power 3 by 2. Again, divide KT with individual terms. You'll have this is EV minus EV by 2, that will give you EV by 2. So EV by 2 minus of plus minus EA by 2, separating the terms to KT plus KT by 2, KT is there na, so you just like this will be like EV minus EA by 2 whole divided by KT plus KT by 2 log NA by 2 pi m h star KT by h square power 3 by 2 divided by KT. So this will be written as EV minus EA by 2 KT plus this KT and KT will cancel up, left over with 1 by 2 log NA by 2 into 2 pi m h star KT by h square. So this is like A log B is equal to log B power A. So you can take this 1 by 2 onto the power. So the equation will be shifted like EV minus EA by 2 KT plus log of the constant term power 1 by 2. Now this will be like exponential A plus B. So exponential A plus B can be written as exponential A into exponential b. So this will be EV minus EA by 2 KT into exponential log this term. So again, exponential and log will cancel each other. So this is a constant term multiplied with a exponential function. Just replacing the same term in density of holes, you'll get a final expression for carrier concentration of p-type extrinsic semiconductor, in which if you see, this is whole power 1 by 2. If you observe that this 2 pi m h star by kt by h square power 3 by 4, it is a constant and exponential function is also a constant. So p is directly proportional to Na power 1 by 2. That is the carrier concentration of a p-type semiconductor is directly proportional to square root of acceptor concentration. So this is all about a p-type extrinsic semiconductor. Now let us see the variation of Fermi energy with respect to the temperature and carrier concentration. So for that, we just need to have an expression for Fermi energy, what we had derived earlier for p-type, that is EV plus EA by 2 minus KT by 2 log Na by 2 into 2 pi mh star KT by h square power 3 by 2. So if you see that at 0 degree Kelvin, EF will be equal to EV plus EA by 2. So at 0 degree Kelvin, the Fermi energy lies just between the, at 0 degree Kelvin, Fermi energy lies just in between the acceptor level to valency level. Now, if you increase the temperature, what happens? Slowly, electrons will excite from valency band to acceptor level, leaving holes in the valency level. So, where the whole concentration is increasing in valency band, that's why Fermi level will shift towards the valency band as the temperature increases. Once all the ionized atoms get ionized, now what happens? It will become stabilized for some time. After that, even increase of temperature makes these electrons to excite from valency band to conduction band. The criteria is as same as an intrinsic semiconductor. So the Fermi level will shift towards the intrinsic Fermi level. If the carrier concentration, that is donor acceptor concentration, is increased furthermore, this shifting towards the valency band will move furthermore, and then the scenario is as same as the before one. So with the increase of temperature, EF decreases slightly as per the equation. As per the equation, if you increase the temperature, what happens? The negative term goes on increasing. So obviously the total term goes on decreasing. So as if you increase the temperature, Fermi energy slightly decreases. So as the temperature is increased, more and more acceptor atoms are ionized, and at a particular temperature, all acceptor atoms are ionized. Further increase of temperature generates electron hole pairs, and the material tends to behave like an intrinsic semiconductor, and the Fermi level gradually move towards the intrinsic Fermi level. Even if you rise the carrier concentration, that is acceptor concentration, also rising of Fermi level towards the intrinsic level will become little bit slower comparable to the before one. Okay, thank you.